Hi, in this video, we're going to look at finding the shortcuts for differentiation for three of our basic trig functions. I'm not going to worry too much with the secant, the cosecant, and the cotangent. I'm going to focus on the sine, the cosine, and the tangent functions and see if we can find what the derivative would be for each of those functions. This is going to test your trig skills. You're going to have to remember some of your trig identities as we go through here. So let's start off with the sine function. Let's say that we've got f of x is going to be equal to the sine of x. Now, before I actually start taking the derivative here, I need to take a look at a couple of limits here, and I want you to test this with your calculator. We don't have a way right now to actually prove that these two things are true algebraically. But what I want you to do for right now, just kind of pause the video for just a second and plug sine of x over x into y1 in your calculator, and then use the tabular method for what we were looking at in limits to see what's happening as this function approaches 0, as x approaches 0. What you should find when you look at the table of data there is that the sine of x over x, as x gets closer and closer to 0, is equal to 1. And then you can test this one as well, cosine of x minus 1 divided by x. Plug that into your calculator and look and see what's happening there as x gets closer and close to 0. You should find that that limit is going to be 0. So I'm not going to prove these right now. We have a method to show that these two things are true. I'm not going to go there just yet. A little bit later we're going to look at a rule called L'Hopital's rule, where we can actually prove that these two things are true pretty easily. Once we're kind of comfortable with working derivatives, that rule is really easy to work with and actually really handy as we need it. Okay, but for right now, we're just going to make the assumption that these two statements are true. Okay, and we're not really an assumption, but I want you to check those on your calculator and verify that those two statements are true. So now, and the reason that I have that is because I'm going to use these two things in my proof of the derivative for the sine of x. Now, unfortunately, we're going to have to go back to the limit definition for this. I know in the last video we tried the quotient rule. We didn't have to do that. We were able to use a combination of the product rule and the chain rule. For this one, though, we're going to have to go ahead and go back to our limit definition of derivative. So, if our function is f of x equals sine of x, then we're going to take the limit as h tends to 0 of the sine of x plus h, as always just replacing the x with x plus h, minus the sine of x, all divided by h. Okay, now there's not any kind of algebra that I can do here right now, but there are some trig identities that I can work with here. If you remember, the sine of the sum of two angles can actually be separated out, and so that's what I'm going to do here. I'm going to take this, and this is what I meant when I said this is going to test your trig knowledge and your trig abilities here. We're going to have to work with there's several identities that are going to come up here. So the sine of x plus h, the sine of an angle plus another angle, is equal to, according to our trig identities, the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. Okay, so the sine of x plus h is equal to all of that right there, using our trig identity, the sum formula for that. And then we can't forget here we've also got minus the sine of x, and all of that is divided by h. Now it looks like kind of complicated things, made it a little bit more difficult to do, but at least now I have individual angle measures to work with here for each one of my trig functions. And so what I'm going to do is I'm going to combine a couple of things together here. I'm going to look at this. I'm going to say, well, if I look at this first term here and I look at this last term here, both of those will have a sine of x in it. And so I'm going to actually go through and combine the first and the third one, put that over one fraction, and then I'm going to leave the second one over h by itself. So I'm going to split this up, and I'm going to say, okay, I have the limit as h goes to 0. I'm going to take the first term, which was sine of x, cosine of h, and then I'm going to take the last term, which was minus sine of x. I'm going to put that over h. And remember, the limit of a sum is the sum of the limits, so I'm going to actually split this up, and I'm going to say that's going to be plus the cosine of x times the sine of h divided by h. And now you can see, and keep in mind here, I split this into two fractions here. This is a common denominator. I can actually just add those back together and I would get back to here. So I'm just kind of splitting this apart so that it's a little bit easier to work with. Now, what I see here is that these two terms both have a sine of x, and so I'm going to factor that sine of x out. And that's going to get me the limit as h goes to 0 of the sine of x, and then that's going to be times, so if I factor out the sine of x away from that, I'm going to get left with the cosine of h minus 1 divided by h. And then the second one here, I'm actually going to evaluate that limit separately, so I'm going to go ahead and put another limit symbol out here. Remember that the sum of the limit is the limit of the sum, and so I have the cosine of x times the sine of h over h. And now I can actually take a look at this and actually do some evaluation based on the two things that I've assumed to be true or that we tested before we started talking about this. Let's first of all look at this first one. Now, we've got the limit as h tends to 0 of sine of x. Sine of x doesn't have an h in it at all. And so that's going to end up being sine of x. Okay, the h doesn't affect the sine of x at all. And then I have the limit as h goes to 0 of cosine of h minus 1 over h. That is this piece right here. The h's in my formula down here are the same as my x's up here. That doesn't really matter. That's a dummy variable. So this whole piece right here turns out to be equal to 0. Okay? Which is going to make this whole first term disappear. It's going to be gone. Don't have to worry about it because I've got sine of x times 0. It doesn't matter what sine of x is, multiplying it times 0. So I've got plus, and now I have the limit as h tends to 0 of cosine of x. Again, cosine of x is not being affected by the h here, and so it's just going to stay where it is. And then I have the limit as h goes to 0 of sine of h over h. That's what I have up here, and we tested this in our calculator and found that that was equal to 1. And so it turns out that all of this simplified down to that went away, and I got cosine of x times 1, which is just cosine of x. And so it turns out that the derivative of the sine function is the cosine function. That's kind of handy. It's going to be easy for us to remember. So if I want to take the derivative of the sine, I get the cosine function. Now, we're going to take a look at the derivative of the cosine function. It actually works very much the same way. You're going to see me do a lot of the same types of things here. The difference is going to be that our separation here is going to be a little bit different because of the identity for cosine of x plus h. So let's go through and take a look at what that would be. Let's say that we're looking at f of x equals cosine of x and see what happens with that. Gotta erase my limit here for this one. Okay, so going back to the limit definition, same thing we were checking a second ago. We're going to take the cosine of x plus h minus the cosine of x, all divided by h. And then I'm going to apply the sum formula for two angles that we're taking the cosine of. And if you remember your trig identities for that, we have the limit as h tends to 0. That's going to be the cosine of the first function times the cosine of the second function minus the sine of the first function times the sine of the second function. So this right here is the expansion of cosine of x plus h using our trig identities, and then I have minus cosine of x. And of course all of that's divided by h. Now, I'm going to do the same thing with this one that I did with the last one. I'm going to combine the first and the third terms together, put them over h. I'm going to leave the second one by itself. Let's see what happens when we do that. We're going to end up with the limit as h goes to 0 of cosine of x, cosine of h, minus cosine of x. We're taking the first term and the last term, putting that over h, and then I'm going to, let's see, now I have a minus. I'm going to leave this as minus sine of x, sine of h over h. Okay, so again, have a common denominator here so I can combine those back together and rearrange the numerator again and get back to where I started. So I'm just rearranging things here. Okay. Now, last time, if you remember, when we were doing the sine function, we were able to factor something out. I have something here. I've got a cosine of x and a cosine of x. I'm going to factor that away. When I do that, that's going to give me the limit as h goes to 0 of the cosine of x times, let's see, when I factor cosine of x away, I get cosine of h minus 1 over h. Okay, pulled the cosine of x away, got left with cosine of h minus 1 divided by h. Again, I'm going to split that limit up. This time, remember, we've got a minus sign here. And I'm going to be taking the limit as h goes to 0 of sine of x, sine of h, divided by h. And now, just like last time, I've got the pieces that I need. I can use the information that we had up here. I know when I take the limit as h goes to 0 of cosine of x, the h is not affecting that, and so I get left with the cosine of x. Then I have cosine of h minus 1 over h. I'm taking the limit as h goes to 0. That matches what I have down here. And I know that that's equal to 0, so that piece of the term is going to go away. And then I have minus, I have the limit as h goes to 0 of sine of x. The h is not affecting that, so I get sine of x. And then I get the limit as h goes to 0 of sine of h over h. That's my top function up here, or my top limit up here. That's going to be equal to 1. And now, the cosine of x times 0, that goes away, and I get left with negative sine of x. So we found that the derivative of the sine function was the cosine function, and the derivative of the cosine function is negative sine. Okay? So now that we've kind of gone through these limit definitions here for this, that's actually a relatively simple derivative to take. Taking the derivative of the cosine is always going to give me negative sine. Taking the derivative of the sine is always going to give me positive cosine. Okay, a couple of pretty easy ones to do there. Now that I've got sine and cosine, let's take a look at the tangent function. I'm actually not going to have to go back to the limit definition for this one, because I know how to write the tangent function as using sine and cosine. So what I'm going to do is I'm going to say, okay, let's say we have f of x equals the tangent of x. I know that that equals the sine of x divided by the cosine of x. And so I have a function divided by a function, and I know what the derivative is for sine, and I know what the derivative is for cosine. And so let's just use the quotient rule and the derivatives that we found for sine and cosine to find out what the derivative for the tangent function is going to be. So f prime of x, using our quotient rule says to take the derivative of the numerator. Derivative of the sine function was cosine, so I have cosine of x, times the denominator, cosine of x, minus the numerator, which is sine of x, times the derivative of the denominator. The derivative of the cosine function is negative sine. Take all of that and divide it by the denominator squared. Okay? So that doesn't look very good. That's kind of nasty looking. But if I look at this again, let's see. Cosine x times cosine x, that's cosine squared x. Negative sine times negative sine is positive sine squared x divided by cosine squared x. And remember your trig identities, we have a really nice one here. The Pythagorean identity says that the cosine squared x plus the sine squared x is equal to 1. So this is 1 over cosine squared x, which is equal to secant squared x. There's our derivative for the tangent function. The derivative of the tangent is secant squared. So those are 3 that we're going to look at. The other 3 we can actually derive pretty easily using the derivatives for sine and cosine like we have here. Again, just using the quotient rule to do that. If I wanted to find the derivative of the secant function, then I would use the quotient rule on 1 over cosine. If I wanted to find the derivative of the cosecant function, then I would use the quotient rule for 1 over sine. And if I wanted to use find the derivative of the cotangent, then I would do cosine divided by sine. And I could find out what each of those are relatively easily. So I'm not going to go through those proofs for you. The three that we have here, the derivative for the sine, cosine, and tangent function, are the ones that you're going to run into most often. If you need the other ones, then you can, of course, convert, like if they ask you to find the derivative of the secant function, then you can convert that to the cosine function and then just differentiate from there. So we can always get where we need to go with just these three basic derivatives here. Okay? As always, I'm going to say that we're going to go back and take a look and practice some of these derivatives later. Once we get all of our shortcuts down, we're going to take a couple of videos and practice a whole bunch of these problems, and then you're going to want to get lots of practice for them on your own as well.